The subject of our paper is bilingualism, advantage in handwritten character recognition, in which we took a deep learning approach for an investigation on Persian and Latin as scripts. Many empirical studies have uncovered the positive effects of knowing multiple languages in learning and recognition. For example, one recent finding suggests that the volume of gray and white matter in frontal and temporal lobe regions of the cerebral cortex are greater in individuals with bilingual experience than monolinguals. The blue curves here are corresponding to bilingual experience, and the red ones are corresponding to monolingual. It has also been shown that learning two languages is very advantageous for mental and linguistic abilities, and also behavioral studies reveal that bilingualism greatly facilitates word learning. In one experiment, a pair of letters was presented for a certain amount of time on a screen, and the participants were asked to respond whether the letters are the same or if they are different by pressing a key on a keyboard. And the results of this experiment shows that whereas for naive observers, complex letter shapes are much more difficult to discriminate than are simple ones, for expert observers the reverse is true. And this effect is referred to as a complexity benefit. So as you can see here in this figure, so HBS stands for high proficiency biscriptal, LBS for low proficiency biscriptal, and MS for monoscriptal. And so both biscriptal groups, these two lines, show a numerically larger complexity benefit than monoscriptal group, which means that as the complexity of a letter increases, their response time for recognizing those letters decreases. So most of the existing computational models for bilingualism are based on SOM, self-organization map architecture, in which they use two SOMs, one for each language, and then they connect these two SOMs through Hebbian learning. So for example, this architecture, which is called SOMBIP, is for a translation task, in which when a word from a language is presented as an input for one of SOMs, the translation of that word in another language will appear from another SOM. In the present paper, we investigate bilingual advantages for handwritten recognition of individual digits which are belonging to two different languages of Persian and Latin. So in the following slides, I'm going to first introduce our methods and the data sets that we use, and then I will present results and make a discussion on the obtained results, and then present conclusion and suggest lines of future works. The whole data set includes Persian handwritten digits which have been collected by Khosravi and Kabir, and they are freely available online. And this dataset consists of 60,000 training images and 20,000 test images. And the original images are in binary format, and they are variable in size. So for our purpose, we had to first rescale all images to fit a 20 by 20 pixel box. which produced gray-valued patterns. Then the obtained images were padded by adding zero-value pixels in such a way that they fit into a 32 by 32 box with a black background. The MNIST dataset, like HODA dataset, consists of 60,000 training images, and unlike HODA datasets, it only has 10,000 test images of handwritten Latin digits. Images were originally grade valued and were centered to fit 28 by 28 pixel boxes, and so we resized them to 32 by 32 while preserving their aspect ratio in order to be compatible with our HODA dataset. Our method is based on using deep leaf network, which is composed of several restricted Boltzmann machines which are stacked together, and the architecture that we use includes 3 hidden layers that have 500 units in the first layer, 500 units in the second layer, and 2000 units in the third layer. And this architecture is the same as was used previously by Hinton and has shown to be robust to small variation in size, variation in the size of the hidden layers. So the RBMs are trained in an unsupervised manner using contrastive divergence algorithm, which was proposed by Hinton. And the moment coefficient that we used was initiated at 0.5 and were for only the first 5 epochs, and then was increased to 0.9. And we also exploited implementation on GPUs, which is based on a mini batch learning scheme. In order to evaluate the performance of the networks after we did unsupervised generative learning, we applied a linear classification module to the deepest hidden layer, that is the third layer. And for the supervised classification task, we use delta rule algorithm. The accuracy of the classification was obtained by computing the average rate of correct responses over all the test patterns. And first, we evaluated the performance of each networks that were trained separately on a single alphabet, and that is our monolingual networks, in presence of 13 levels of visual noise. The visual noise were obtained by adding zero mean Gaussian noise with different levels of standard deviations, which were selected from 0.01 to 0.4. And here you can see examples of the noisy images from the HODA dataset and MNIST dataset. To assess the significance of the results, we approximated a logistic function on each of the 10 curves obtained from 10 trained networks. We then performed t-tests on 2 sets of slopes of curves which were associated to the obtained performance illustrated by each curve. So this figure illustrates the average accuracy of classification of digits of each data set in presence of noise, and the increase of, as you can see, the increase of noise level attenuated the classification performance. So these are the performance on our monolingual networks, Latin dataset and Persian dataset. Next, we simulated bilingual individuals and compared their performance with monolingual networks. Bilingual knowledge was built by using the training sets of both scripts simultaneously. Examples of receptive fields of the third layer obtained from the train phase of each network are visualized through these figures. And as you can see, while the receptive fields of the output layer of the monolingual networks are very similar to the original digits, the receptive fields corresponding to bilingual individual contains much more complicated patterns because this network is trained using both data sets. We also compare the performance of the bilingual networks on each dataset, and again we can see that the performance of classification is decreased in presence of noise, but there is no noticeable difference between the slope of these two curves. Next, we compared bilingual bilingual network performance with monolingual performance, and so the red curves are corresponding to bilingual network performance, and the green one is corresponding to monolingual Persian dataset, and the blue one is corresponding to monolingual Latin dataset. And our results indicates the superior performance of bilingual networking recognition of each digit set, even in presence of different noise levels, and also the t-test analysis shows that there is a significant difference between these two curves for the monolingual and bilingual network performance. So in summary, in this paper we simulated visual symbol recognition in monolingual and bilingual individuals, and we used deep neural networks using stacks of RBMs. So as I said, in all of our experiments we used a 3-layer deep belief networks, which was composed of stacks of restricted Boltzmann machine. We found that bilingual networks, which were equally exposed to different writing scripts, had a higher performance in digit recognition compared to the monolingual networks. In particular, our results are in agreement with the studies that support the positive influence and the benefits of learning more than one language. And we also showed that learning the statistical features of two different data sets increases the ability of handwritten digit recognition even under noisy conditions. So for future work, one exciting avenue would be to more systematically compare simulation results with empirical data collected on human observers. So for example, the confusion errors of the model can be correlated with empirical confusion matrices. So for example, between Latin and Arabic alphabets and so on. Moreover, it would be informative to more carefully investigate how learning over multiple datasets could facilitate knowledge transfer across similar perceptual domains. Thank you.